Hello friends. In the last class we looked at the hydrodynamic details of internal flow, and we understood that the flow can be divided into the developing region and the developed region. The developing region being where the velocity profile builds up and keeps undergoing change with x. And in analogy with boundary layers, we were actually looking at flow between two parallel plates and understood that it's as if the boundary layer is developing independently from the two plates and eventually meeting on the mid-plane. But we also understood that it's a little more than that, because the total mass flow rate remaining constant, the development of the velocity profile ensures that near the wall the velocity is decreased, and therefore near the center the velocity increases. And we understood that in the fully developed region the velocity profile stops undergoing any change, and the velocities are completely parallel to the axis of the flow, and so you will get v is equal to 0 and u as a function of r, or u as a function of x, and u as a function of y, and that's how we derive the details of the velocity profile and therefore the shear stress and pressure drop. In today's class we will be looking at the development of the thermal boundary layer, so to say, or thermally developing or developed flows. So just like the velocity profile, the thermal boundary layer also grows from both the walls. If I look at the parallel plates channel, it grows from both the walls and meets on the midplane, and after it meets, something becomes constant. We all understand that when there is heat transfer, the temperature profile cannot become constant, because the temperatures undergo a change because of heat transfer. So it's not correct to say, unlike in the case of velocity profile, that in the fully developed region the temperature profile becomes invariant with x. It is not correct. But then something becomes invariant. What is it? That is something that we will see today. So let's go to the whiteboard and start understanding what becomes constant with full development. So we'll look at thermally developing hydrodynamically fully developed flow. Okay, and we are still looking at laminar. Okay, so what do we mean by whatever we have written here? So suppose I have a parallel plate channel, or any duct for that matter. It could be a circular pipe also. So suppose this is the inlet plane where x is equal to 0. Then what we are saying is that from the inlet plane itself, the velocity profile is fully developed. So you will have the parabolic velocity profile, that is u versus y. It's the same at all locations, parabolic profile. So basically we said that hydrodynamically fully developed flow, so you have a parabolic velocity profile. So this is u as a function of y. Okay, throughout the pipe. So we are just drawing it above so as to make it clear. But the temperature profile, let's show it below. So suppose I am looking at, let's say, constant wall temperature, or it could be variable wall temperature also. So let us say T wall is the wall temperature, and let's say Q dot double prime wall is the heat flux through the walls, and let's say this is the center plane. Okay, so then the temperature profile, let's say it's constant wall temperature, and let us say the inlet temperature is Ti, then at the inlet, because of the kind of velocity profile, temperature profile development, okay, in this region there is a certain thickness over which the temperature profile is changing between inlet temperature and the wall temperature. Okay, so there is a variation from inlet temperature to wall temperature, and then the rest of the region, the temperature is equal to Ti. Let's say this is Ti and this is T wall. So this is the way the temperature profile is in this region, and after it develops fully, I would have, let's say this is T wall, and there will be a smooth temperature profile. Okay, it would have forgotten the value of Ti, but it will become smooth. So there will be a mean temperature in this region. Let's say this is Tm and this is T wall. Okay, and as the flow goes, so this is the temperature profile here. As the flow goes, suppose the heat flux is from the wall to the flow, then even if the temperature profile, the wall temperature remains constant, the bulk temperature will go on increasing. Okay, and so the mean temperature, rather, this mean temperature would have come closer here. So the curve would be more shallow. Okay, and sorry. Okay, and the mean temperature would have moved, Tm would have moved closer to T1. Okay, so the mean temperature has increased from here to here because there is heat flux on inside. So this would be the temperature profile. So this is the way the flow is going, but there is something which is becoming invariant in the region between in the region after the location x is equal to, let us say, LET. We had written LE for the entrance length hydrodynamic, so we'll write LET for the thermal entry length. So let's the T be capital. So LET is the location at which, let's say, the boundary layers meet, or so to say, the entrance effects are completely eliminated. So from that you have thermally fully developed flow, and thermally developing flow here. Okay, so in order to understand what becomes constant in this region, let us try to do a little bit of analysis. So suppose I take any segment of a small then the distance del dx here, and write down the energy balance for that. So there is, let's say, some heat flux. This Q wall could be a function of x, okay, and the T wall also could be a function of x in the most general case. So then, if m dot is the mass flow rate of the flow that is going through this, which has a mean velocity, let's say u bar, okay, so this mean velocity here is u bar, okay, then this m dot would actually be equal to rho u bar into A, where A is the cross-sectional area of the duct. So if it's a circular pipe, it's pi r naught square, and if it's a parallel plate duct, it is per unit depth, it will be the total width between these two. In the yesterday's class, in the previous lecture, we wrote it as D, so that could be D. Okay, so that is the rho u A. So that m dot multiplied by, if specific heat is taken to be constant, Cp, multiplied by the change in the mean temperature between these two locations. So suppose this location, it is Tm at x, and this is Tm plus dTm, then the change is dTm in this region, and that would actually be equal to, by energy balance, Q dot double prime wall multiplied by the area over which the heat transfer is happening, which will be perimeter into dx. Okay. So that is the area over which the heat transfer is happening. So this heat flux multiplied by this area is equal to this. So if I rearrange this expression, then I'll get this m dot, I write it as rho u bar A, then I'll get dTm by dx. This dx I'm taking it this side, and this m dot Cp I will bring it here and expand it. So this will be equal to q dot double prime wall divided by, this will be rho Cp u bar into perimeter divided by area. Okay, so this is the expression that I'll get for the rate of change of mean temperature with x. Okay, so now this can now actually be also determined by taking elemental areas in the region and integrating it. So actually I can define this mean temperature as follows. So this Tm is nothing but, suppose I have a duct with varying temperature, some arbitrary temperature profile in this and a certain velocity profile. Then at any elemental location, suppose this is the total area and this is an elemental segment of that area dA. Okay, then actually this can be written as, so the total energy that is there at any section is determined using the mean temperature of that section. So it will be m dot multiplied by Cp multiplied by Tm at any x actually should be equal to integral of rho u dA, which is the m dot of that small element, multiplied by Cp into temperature at that location. So if I rearrange this, and so rho and Cp are constant, I can take them out and bring them this side, and this I can write it as rho u bar A. Okay, then if I rearrange this, I'll be able to get Tm at any x would be equal to this rho and Cp get cancelled. So I would get this u bar A coming down 1 over u bar A integral over the area of this rho and Cp are gone, it will be u T dA. Okay, so this is the definition of the mean temperature. So the mean temperature is also called the bulk temperature. So the Tm is actually the mean temperature at any section. So if I take this section would have some temperature profile and it will have certain mean. So if I have, let's say this as the temperature profile here, the mean temperature of this location will be similar here. So this is the temperature axis and this is the y-axis. Okay. So suppose the temperature profile is something like this. The mean temperature will be somewhere here. Okay, that's the thing that we have defined. So that will be determined by the velocity at that location and the temperature, because we are actually doing a mass weights average. So this is called the mean temperature, and we can define a different mean temperature for every x location. So as we go with x at different x values, you can have different mean temperatures because the heat transfer is happening in the x direction, and therefore the mean temperature will change with x. Now this mean temperature is also sometimes called the bulk temperature. So some books use the temperature, use a symbol TB for this temperature. So, and it's also called the mixing cup temperature. It's a very interesting term that people use. So it's as if whatever flow is coming at this plane, if I just pour it into a cup, then thoroughly mix it, I'll get the mixing cup temperature. So that temperature would be equal to this temperature that we get here. Okay. So that is the meaning of the mixing cup temperature. It's as if we poured the flow into a cup and took the mean temperature. So this is the way we define the mean temperature. And now if I go to the energy equation for fully developed flow, and do an order of magnitude analysis in order to estimate what would be the behavior of the various terms. So the energy equation is U del T by del X plus V del T by del Y is equal to alpha, this rho Cp will go down there, alpha times 1 over R del by del R del T by del R. We are writing for a circular pipe now. Okay, yesterday we wrote it for a parallel plates channel, so today for a change, let's write it for a circular thing. It's going to be quite similar. Del squared T by del X squared, which is the axial conduction term, is the radial conduction term. So this is the equation. Now for the fully developed region, since we have said that the flow is hydrodynamically fully developed, V is going to be equal to 0, and therefore this term will go off. So U del T by del X will be the term that's there on the left side, and on the right side you have alpha times this whole thing. So let's do an order of magnitude analysis for this. So the order of magnitude analysis would mean the U is going to be of the order of U bar, because it varies between 0 and 2 U bar or whatever in the circular pipe. So it's of the order of U bar. Del T by del X can be taken to be of the order of dTm by dx, okay, which is given by the expression that we just derived in the previous page. So dTm by dx will be given by this expression. We'll come to that when we come there. Then del T by del R will be of the order of T wall minus T mean divided by D. Okay, it's actually of the order of R, but I'm trying to write in terms of diameter, so it's D, and this del square T by del X squared will be 1 by X times del T by del X, which will be this. So then this whole equation can be written in this form: U bar into dTm by dx. I can write it as Q wall double prime multiplied by or divided by rho U bar Cp multiplied by perimeter by area. Perimeter by area is actually pi d divided by pi d squared by 4. So it will be of the order of 1 by d. Okay. So that is the first term, and this is of the order of, on the right hand side I would get alpha times this term. This actually is going to be this divided by d square. T wall minus T mean divided by d squared, because there is del square T by del R square in some form. That is the first term. And the second term is going to be of the order of 1 over X into Q dot double prime divided by rho U bar Cp into D. Okay, so this is the order of magnitude. Now let's take these orders of magnitude, divide multiply the whole equation by the inverse of this, so that this term becomes 1, because the radial conduction is always going to be present. That is the basic premise of the entire study of internal flow heat transfer. The wall is heated or cooled, and therefore there is heat transfer inside the pipe. So convection inside the pipe or convection inside the duct is studied primarily with reference to this term. So this term is always present. So let's normalize the terms with respect to this. So multiply the whole equation by d squared by T wall minus Tm. So let's do that on the next page. So d squared divided by T wall minus Tm multiplied by, there is a Q dot double prime wall divided by this term, the U gets cancelled out between here and here. So there is a rho Cpd, and you write rho Cpd. So this is the left hand side is equal to, this term becomes 1. This term becomes d squared by T wall minus Tm multiplied by 1 by x times q dot wall double prime divided by rho u bar Cp d. Right? So this is the expression that we have obtained. Now let's simplify this. So we understand that the wall heat flux is written at any location, at any x, as H at that location multiplied by T wall minus Tm, and therefore Q dot divided by T wall minus Tm would actually be H. Okay, so then this 1d gets cancelled. Okay, so there is this rho Cp, and I multiply and divide by K. So then what do I get? I get H, because Q wall by T wall minus Tm is H, and B, and multiply and divide by K. So I get HD by K into K by rho Cp. Okay, this is of the order of 1, and okay, what did I miss? The m dot. Okay, this alpha. All right. So this alpha has to be written here, right? So that's something which we have missed out. Okay, so you actually have to multiply the whole equation not by d squared by t wall minus tm, but d squared by t wall minus tm alpha. So when I do that, okay. So this alpha gets cancelled here, and this alpha can be opened up as K by rho Cp. So this rho Cp actually gets cancelled here. There's only this term there. Okay, so HD by K is here, and this is 1, and this becomes again 1d would get cancelled. So this would become HQ divided by T wall minus Tm into D divided by K into, I multiply and divide by K. So I'll have a K divided by rho Cp into 1 over rho u bar d. U bar x, sorry. That's one term. Okay, now let me try to multiply and divide this by a new, okay, so mu rather. So that's the extra row that I have written here. Okay, so this rho Cp is only this, so it's only a u bar x, and I multiply it and divide by a nu. Okay, so this being alpha, I get a nu by alpha here, which is a 1 by PR, and you get a ux by nu in the inverse, so it will be a 1 over Rex. Okay, so what do I get here? I get this HD by K is NUD is of the order of 1 comma this will be again NUD divided by REX PR. So this is the order of magnitude that you get from the energy equation. So in the case where REX PR is much greater than 1, because in the fully developed region it's at a larger X anyway, and if PR is large enough, then you get an REX PR much greater than 1, then this term is negligible as compared to this. Okay, so in the energy equation it is comparison of this term with respect to this term. So this is of the order of 1 and this is of the order of Nu divided by REX PR. So when REX PR is much larger, then the second term is negligible. So then NUD by actual conduction, NUD by REPR is much less than 1. Okay, and in which case this term can be neglected, in which case NUD is of the order of 1. Okay, so this is the interesting result that you get, that as the flow goes to full development, which is REX PR larger than 1, much larger than 1, you get the NUD of the order of 1. We have not invoked any condition here that the heat flux is constant or wall temperature is constant or any of that. So for all kinds of internal flows, after the flow becomes fully developed, the order of magnitude analysis tells me that the Nusselt number becomes independent of X. Okay, so what is the Nusselt number? It is actually HD by K, and D and K are anyway independent of X. So H, the heat transfer coefficient, becomes independent in thermally fully developed region. So all of this analysis that we did basically points out to the fact that when I say thermally fully developed flow, I actually mean to say that the heat transfer coefficient has become a constant with X. So with actual movement, as I go beyond the point where the two the inlet effects or the entry effects get over, so if I go back to the first slide, I'll see beyond the point where these boundary layers meet, if I would like to call it that, or even inside a circular pipe, wherever the entry region which is unaffected, the inlet region here which is unaffected by the region here which is unaffected by the presence of the walls, when that region completely is eliminated, then the thermally developing region is over and you get the fully developed region. And in the fully developed region, what we have said is that your Nusselt number becomes of the order of 1, so you get H becomes independent of X, and you get a single number for the Nusselt number which is in the order of 1, which is like between, let's say, between 1 and 10. That is typically the number that you get, or 0.1 and 10 if you like. That is what you would get. Okay. So now once we have learned this, that thermally fully developed flow basically means flow with a constant heat transfer coefficient, then we can analyze the internal flows in the fully developed region using that concept. So what do you then write? You write that H, which is Q dot double prime wall divided by T wall minus Tm, is a constant. Okay, it doesn't vary with X or Y. So what does it mean? It means that if Q dot double prime wall is constant, it implies that in this, because this is a constant, if this is also constant, then this becomes a constant. T wall minus Tm is constant, and when I say constant, is independent of X, the flow direction. Okay, so if I try to plot that, okay, X and temperature. So if I have a pipe which is heated from outside at constant heat flux, that's what we have said, Q1 is constant. Then basically if I have some inlet temperature, that inlet temperature will go on increasing. So after the fully developed part in this region, it's anyway going to increase, and its T wall minus Tm is going to remain constant. And since Q wall is a constant, if I go back to the term that the expression that we derived for dTm by dx, this dTm by dx, since Q wall is a constant, all the rest is also a constant. The dTm by dx becomes a constant, or Tm increases linearly with x. So the Tm would go linearly with x like this. And since the heat is coming from the wall temperature has to be higher than that. And since T wall minus Tm is a constant, the T wall is also a constant, a straight line with this, so that this T wall minus Tm is a constant. That is, it becomes independent of x. So this is the understanding that we get from the expression that we just derived. What happens when the wall temperature is constant? Then the plot will look something like this. The T wall is a constant. Okay, with x, the T wall doesn't change. So the T mean, since the heat flux is coming from since the T wall is constant, and like if we take a condition where the fluid temperature is lower, so the heat is coming into the fluid from the wall, just like in the other case. So if I have the tube like this with T wall is equal to constant, and you have a Ti less than T wall as the inlet temperature. So then if the fluid temperature starts at Ti here, it will asymptotically approach T wall. So this will be T mean. The T mean will be Ti at the beginning, and it will increase and asymptotically approach T wall. So what does it mean if it asymptotically approaches T wall? Then as you go with increasing x, the temperature difference that's available for the heat transfer will decrease, and therefore the heat transfer will also go on decreasing. But then you are saying that the h is a constant, which basically means that as T wall minus T mean goes on decreasing, the Q wall will also decrease, such that the ratio of these two in the fully developed region, the ratio of these two, that is Q wall and T wall minus Tm, becomes a constant. So that is the thing that you get. So as this approaches 0, the difference between T wall and Tm approaches 0 asymptotically, the Q also approaches 0 asymptotically, such that the ratio of the two remains a constant. Okay. So that is the understanding that we get by constant wall temperature. And you can have any other kind of boundary condition also. For example, you can have a boundary condition in which the Q wall is varying with x. Okay, so this Q wall can be a function of x. Okay, in which case the T wall minus Tm will also be a function of x in such a way that the ratio of the two becomes a constant. Okay. So the T wall minus T mean would actually be equal to f at x divided by h, which is a constant. Okay, so it will be another constant. So these two will have the same trend with just a ratio. Okay. So this is basically what we have derived, irrespective of what the boundary conditions are. The fully developed region is a place where your heat transfer coefficient becomes a constant. Okay. So hydrodynamically fully developed region basically means your velocity profile doesn't change any further, but the temperature profile will have to change in order to accommodate heat transfer. So it goes to a state where h becomes a constant, or the heat transfer scales with T wall minus T mean. So if I define the temperatures with this T wall minus T mean as a scaling parameter. So suppose I say theta, which is a non-dimensional temperature, is equal to, let us say, T minus T wall divided by T mean minus T wall. Okay, so this is a way of defining a non-dimensional temperature. T minus T wall by T mean minus T wall. Since T wall minus T mean or T mean minus T wall going to scale with the heat flux, that will become a similarity parameter. Then you will get del theta by del x is equal to a constant after fully development of flow. Okay, this is basically what you will get, that the temperature differences will all scale with T mean minus T wall. So if you normalize with respect to T mean minus T wall, then this becomes a constant. This is you can see this to be valid in both cases. Here T mean minus T wall is a constant, so temperatures anywhere in the flow will only linearly vary with x in the same fashion. At the wall it is varying like this, and inside the flow it may vary in this fashion, and therefore all of these are parallel to this. So if I write T minus T wall by T mean minus T wall at any of this location, that would become independent of x. So that is in this one. In this case also, since the temperature differences scale with T mean minus T wall, all temperatures will actually scale between these two in this fashion. So if I normalize with respect to T mean minus T wall, it becomes a function which is independent of x. So del theta by del x is okay. Del theta by del x is actually a 0. Okay, so this happens after the middle flow. So if I normalize the temperature with respect to T mean minus T wall, then I get a temperature profile which is independent of x, and that is what I would get, and this theta will be solely a function of r. Okay, so we'll use this in getting the solutions of the various cases. Let me solve the simplest of those cases. Laminar pipe flow with Q dot double prime wall is constant. Okay, and REXPR much greater than 1, so neglect axial conduction. That is del square T by del x square term gets neglected. So if I do this, then I get U del T by del x is equal to alpha into 1 by R del by del R of R del T by del R. Okay, so this is your governing equation. Now, since in the fully developed region, okay, in the fully developed region, of course, resources in the fully developed region of temperature. So this is in fully developed velocity region, so V is 0, and axial conduction is neglected, so you get this term. In the fully developed region of temperature, del T by del x scales as, or this is equal to dTm by del x dx in the case of constant wall flux. Why? Because as we showed here, any temperature at any location, any temperature at any radial location, it goes as a straight line parallel to this. So del T by del x at any location will be actually equal to dTm by dx. The slope of the two will be the same. So I can use this. So what will come here? I'll get a U dTm by dx is equal to alpha times 1 over R del by del R into R del T by del R. Okay. Now I substitute for this dTm by dx for a circular pipe. So for a circular pipe, perimeter divided by area is pi d divided by pi d squared by 4. So I'll get pi gets cancelled, 1 d gets cancelled, I get a 4 by d. So that I can substitute here. So it will be u multiplied by q dot double prime wall, this is a constant, into 4 divided by rho u bar cp to d. So this is your expression for the left hand side. Now I can take out the u by u bar from this one, okay, and then the rest of it is a constant. 4 q dot double prime divided by rho cp d is a constant. This is equal to alpha times, and if I normalize this side with respect to what I wrote here, so t minus t wall by t mean minus t wall, then I'll get a t mean minus t wall out here, and I'll get a r naught square out here. If I can normalize r with respect to r naught, then actually if I say r tilde is r by r naught, and theta is equal to t minus t wall divided by t mean minus t wall. Okay, so I can put that into this expression. So then I'll get 1 over r tilde del by del r tilde into r tilde del theta by del r tilde. Then confirm this. This theta is t minus t wall by this one, and t wall being a constant, del by del r of t wall is 0, so you can write that. So this is t minus t wall divided by t mean minus t wall, and since t mean minus t wall is independent of r, I can take it out and write it here. So multiply and divide by t minus t wall. Similarly, the 1 over r naught, 1 over r naught. So this r naught can get cancelled. There are 2 r naughts otherwise here, so those r naught square will come here. So this is your expression. So what I can do, this u by u bar, if I write from the velocity profile, u by u bar is equal to okay. So u by u bar I can write for a pipe flow as twice 1 minus r tilde square, because it is 1 minus r by r naught the whole square. So this is the expression. So if I substitute that here and take all of these constants to one side, this will become a differential equation in r alone. So what will I get? This r naught square and this d, I can write it as 2 r naught. Okay. So then you will get 2 into 1 minus r tilde square multiplied by 4 q dot double prime wall divided by rho cp into 2 r naught. Okay, this 2 will get cancelled, and let me bring this term also to this side, so it will become r naught squared divided by, I'll write it as k by rho cp, the alpha, okay, and multiplied by tm minus t1. Okay, so this whole thing right on this side will become 1 over r tilde del by del r tilde of r tilde del t by del theta by del r. Okay, now let me simplify this expression. This rho cp will get cancelled with this rho cp. 1 r naught will get cancelled with this 1 r naught. This q double prime divided by tm minus t wall will be the negative of h, because h by t wall minus tm is q dot. H into t wall minus tm is q dot. So when I divide this, I get a minus h. So I get this 4 is there. So this will be minus 4h into R naught by K. Okay. So 2 R naught I can write it as a D. So minus 2hd by K is what I get, multiplied by this 1 minus R tilde square. Okay, hd by K is Nusselt number with respect to D. So I can write minus 2 NUD into 1 minus R tilde square is equal to 1 by R del by R tilde del by del R tilde to R tilde del R tilde del theta by del R tilde. Okay, now I can take this NUD is a constant with respect to R. It doesn't change with R. So I can now integrate this. This R I take it here. So it becomes R tilde minus R tilde cube. And when I integrate with respect to R, this dv dr, so I'll get R tilde del theta by del R tilde is equal to minus 2 NUD multiplied by this R, when it's integrated, gives me R squared, R tilde squared by 2 minus this R squared into R cube will give me R tilde to the power 4 by 4 and plus some constant C. Let's say C1. Now, if I apply the first boundary condition on theta, okay, what happens when R tilde equal to 0? R tilde equal to 0 is the center line or the axis at which the temperature gradient del theta by del R should vanish. So at R tilde equal to 0, del theta by del R tilde is equal to 0. Actually, this del theta by del R can be written as a total derivative because theta is only a function of R. We have already shown that. But anyway, so if this is 0, this implies that C1 becomes 0. Okay, because this is 0 and these two are also 0. So this is 0. Then if I go back, this I divide by R tilde and del theta by del R will come and I have to integrate. So I get a theta. So theta will actually be equal to minus 2 NUD multiplied by so there is a R by 2 when I divided by the R, this R comes here, this R squared by 2 becomes R by 2. So that when it is integrated, it will become R squared by 4 minus this becomes R cubed by 4. So it will become R to the power of 4 by 4 into 4 is 16. So R to the power of 4 by 16 plus C2. So this is your next constant you get. So you use the next boundary condition at R tilde equal to 1. Okay, so at 0 we have used. So what happens at R tilde equal to 1? R tilde equal to 1, T is equal to T wall. Okay, so although T wall is not a constant in this case, but T is equal to T wall. So your theta, because it is T minus T wall by T mean minus T wall, theta is equal to 0. Which gives me 0 is equal to minus 2 NUD multiplied by 0. Wait a second. This is R is equal to 1. So it's not 0, but it becomes 1 by 4 minus 1 by 16. So it will become 3 by 16 plus C2. So I get C2 is equal to minus or plus 2 NUD multiplied by 3 by 16. So if I substitute that here, then I'll get theta is equal to 2 NUD multiplied by 3 by 16 minus R squared by 4 plus R to the power of 4 by 16, and this multiplied by 2 I get, this is NUD into 3 by 8 minus r squared by 2 plus r to the power of 4 by 8. Okay, so this is the expression for theta that I get. Okay, so this theta, this is not r but r tilde, sorry, this I've been missing the symbol tilde here. Yeah, this is r tilde. Okay, so that is the temperature profile for theta. Once I have got this, then I can write the expression for temperature. Theta is T minus T wall divided by T mean minus T wall, and therefore and that is equal to NUD into 3 by 8 minus r squared by 2 plus r to the power of 4 r to the tilde r to the power of 4 by 8, and therefore I can write T is equal to T wall plus or T wall minus Tm into NUD into 3 by 8 minus r tilde squared by 2 plus r tilde to the power of 4 by 8. Now from this I can actually say Tm is equal to integral u T dA over the area divided by u bar A, and this u, I can take the u bar into the integral and say it is 1 by pi r square, pi r naught square into integral u by u bar multiplied by this T into 2 pi r dr. Okay, and integrated from 0 to r naught. Now if I write it in terms of r by r naught, then I'll be able to write this as 2 pi r tilde dr tilde, and there will be a r naught square that will come. So this r naught square will get cancelled with this, and this pi will get cancelled with this. So, and now I can substitute for u by u bar as 2 into 1 minus r tilde square. Okay, and I can substitute for T is equal to in terms of r tilde. So I can substitute for this and this in terms of r tilde multiplied by 2 r tilde dr tilde, and integrate this between 0 to now r tilde equal to 1. This will be r tilde equal to 0 to 1. So in this, if I integrate, there is nothing that remains here. The Tm equal to this, if I use this, then I will typically get all of this will get cancelled out, the T wall minus T minus T wall. I can integrate and get it in terms of T mean minus T wall, and typically it will lead me to 1 is equal to 11 by 48 into NUD. So this NUD that is here will stay here. This whole, the rest of it will get integrated to this. So the T wall minus Tm cancel out to get 1 here, and the rest of it will become 11 by 48, which will basically tell me that NUD is equal to 48 by 11, which is 4.363. This is the number that I get. Okay, so this is the formula or the expression for the constant result number that is going to result in the fully developed region of circular pipe in which there is uniform heat flux on the wall. The result would change if slug flow is used. That is, in a condition where the velocity profile is not a fully developed parabolic profile, but in the entire region of fully developed thermal flow, you get thermally fully developed flow, we assume u is equal to u bar in the entire cross section. or u by u bar is equal to 1. So this u by u bar becomes 1 here, as well as in a place where we used u here, this u by u bar, this also becomes 1 here. Okay, so then this whole thing integral becomes much simpler, and you get an NUD is equal to 8. Okay, so this is for velocity remaining uniform in whole pipe equal to u bar. Okay, so this is the case of slug flow. So we call that a slug flow because the whole flow goes like a bullet or a slug without any change in shape, and that's the reason why it's called a slug flow. Okay. So for constant wall flux, so this both of these are Q dot double prime wall equal to constant. Okay, in the same way actually, but the algebra becomes a little bit more complicated when I have the constant wall temperature condition. The Nusselt number NUD can be derived to be equal to 3.66. Okay, and for parabolic flow, that is u by u bar equal to twice 1 minus r tilde square, then you get this, and NUD equal to 5.77 for slug flow. Okay, so parabolic flow means u by u bar is twice into 1 minus r tilde square, and this is u by u bar. Okay, so I'll close this topic here just to give you an expression for LET. How do I evaluate LET? When Prandtl number is much less than 1, if I have a pipe like this, okay, when Prandtl number is much less than 1, the thermal boundary layer is much thicker, so the entry length for the temperature would be much smaller as compared to the entry length for velocity. So the velocity, this will be LE and this will be LET. And we can find that this LET expression can then be obtained using the low Prandtl number boundary layer result of delta T by X is of the order of RE X PR whole to the power of minus half. Okay, so with this, in the same way as we can derive for delta, if I say at X is equal to LET, delta T equal to D by 2, then I'll be able to derive this, or this is of the order of D, then I'll be able to write LE by D is of the order of RE PR. Okay, so this is something that I'll be able to derive, and even when Prandtl number is of the order of 1 or Prandtl number is much greater than 1, in the case of boundary layer flow, the thermal boundary layer will be small and the velocity boundary layer will grow much bigger than that. So I can write delta is much greater than delta T if Prandtl number is much greater than 1. But we cannot say this for the pipe flow because the delta cannot grow beyond the D by 2, and after that it just freezes at D by 2. So in the entire cross section or in the entire thermal boundary layer, the velocity u is always of the order of u bar and never u bar multiplied by delta T by delta, which is a very small number in the case of flat plate boundary layers. here it will be of this order, and therefore the same expression will also hold good, and therefore this same expression will also hold good for the Prandtl number of the order of 1 or much greater than 1, because the dependencies don't change between Prandtl number much less than 1 and much greater than 1. So if I compare this with the expression that I got for, this is LET, sorry, and the expression that I got for LE by D is of the order of RED is what we have got. So the ratio of these two will be LET by LE is always of the order of Prandtl number. Okay. So if Prandtl number is much less than 1, the LET will be much smaller than LE, and if Prandtl number is much greater than 1, LET will be much larger than LE, and Prandtl number is of the order of 1, LET will be of the order of LE. So that is where we will stop here. We'll start with developing flows, some analysis in the next class of flows which are hydrodynamically fully developed but thermally developing, and then simultaneously hydrodynamically and thermally developing flows. We'll look at some results for that, and then we will move on to turbulent internal flows. Okay, so at this moment we'll stop with this and look at the remainder in the next class. Thank you.